There is this beautiful result in abstract linear algebra that says that a vector space, a finite dimensional vector space, is canonically isomorphic to the dual of the dual. The isomorphism between the vector space V and its double dual is defined as follows. For every V, I want to map it to an element psi of V that is in the double dual. So it's a linear map from the dual space to the field F. And how do we define psi of V? Well, psi of V takes as input elements of the dual space, and it sends an element of the dual space to that element of the dual space evaluated at the vector V. And one can show, and I have shown this in some of my videos, that this map, this natural canonical map, is an isomorphism. Now, what I want to talk about in this video is the following question. Somebody asked me, what is the inverse of this map? And that is a great question. And in fact, once we have proved that this is an isomorphism, the surjectivity of this map tells me that every single element of the double dual is one of these. It's surprising. It's surprising that every map, every linear map from the dual space to F is actually just evaluated at one fixed element V. But this is what the theorem says, that isomorphism, that is what it says. So the inverse map is as follows. Take any element of the double dual, then it comes from one V, so you send it back to that V. So let's turn this around and let's prove, without having proved yet that isomorphism, let's prove that the double dual is actually all formed by elements of that shape. So what we want to show is that every element of the double dual is one of those psi of V. So let's do that. Let's start with any basis of the finite dimensional vector space V, and let's define psi of Ek to be those elements of the double dual that are just evaluating elements of the dual at Ek, at those basis elements. Now, I claim that those maps, the ones that are just evaluating at basis elements, they're actually a basis of the double dual. For suppose that there is a linear dependence between them, then I can evaluate at any phi, and I get this equality for any phi in the dual. And if that linear combination is 0, then, well, I know what psi k of phi does. It evaluates phi at Ek, and phi itself is a linear map from V to F, so I can use linearity to bring everything inside of phi, and now that, those lambda k Ek is a vector V that is in the kernel of phi for every phi. But if every element